In this lesson, we are going to look more at finding limits analytically. So at the start of section 1.3, we are given a table with all of these properties for limits that are very helpful. But when we do the quotient rule, we have to avoid a denominator of 0. So what if we have some expression that when we plug in the x value, we're getting 0 over 0? What do we do then? Because we remember that 0 divided by 0 is indeterminate. We don't know what it equals. But we are also trying to look at the behavior of our expression near a particular x value. So we're not like at that x value, we just want to be close to it. So what we are going to do when you find your limit looking like 0 over 0 is to rewrite the expression. So we want it to be an equivalent expression, but taking care of the fact that we get 0 over 0. And the way that we could do that is factoring or maybe rationalizing the numerator or denominator. So let's look at an example first where factoring can help us determine the limit analytically. So a rational expression is when you have a polynomial divided by a polynomial. So let's look at the limit as x goes to 3 of x squared minus 9 over x minus 3. And if I just let x equal 3, the numerator would be 3 squared minus 9, or 9 minus 9, or 0. And my denominator would be 3 minus 3, or 0. So I've got 0 over 0. But I can factor the numerator. X squared minus 9 is a difference of squares, and I can factor it as x minus 3 times x plus 3. And in the denominator, I have an x minus 3. And so we can, near x equals 3, cancel the factor of x minus 3 in the numerator and the denominator. And so this is the same as the limit as x goes to 3 of x plus 3. And we know that this is going to equal 3 plus 3, which is 6. If we were to go ahead and graph the expression y equals x squared minus 9 over x minus 3, we know that the domain is everything except x equals 3. And because x minus 3 is a common factor in the numerator and denominator, the graph is going to have a hole when x equals 3. So the reason we get a hole is because x minus 3 is a common factor of the numerator and the denominator. So let's do another example. In this example, we have a radical. We have a square root. So we're doing the limit as x goes to 0 of x squared plus 9 minus 3 over x. And if we let x equal 0, the numerator would have 0 squared plus 9, which is 9. Square root of 9 equals 3, and 3 minus 3 is 0. So the numerator simplifies to 0, and the denominator is 0. And that's an indeterminate. We don't know what that is. When we have a square root, we're going to rationalize. And this is taking advantage of difference of squares. So I'm going to multiply by the radical conjugate, which is the same two terms that are in the numerator, but instead of subtraction, I'm going to have addition. So when we do the multiplication in the numerator, square root of x squared plus 9 times the square root of x squared plus 9 is just x squared plus 9. Then we would have a 3 times the square root of x squared plus 9. When I multiply these inside terms, I get a negative 3 times the square root of x squared plus 9. Those add together to equal 0, and then I'm left with a negative 3 times a positive 3, which is just negative 9. And so our expression simplifies to the numerator being x squared plus 9 minus 9, and our denominator is just x times x squared plus 9 plus 3, and our numerator just simplifies to x squared. And I see that there is a common factor of x in the numerator and the denominator. So I'm going to cancel that and cancel one factor of x out of the numerator. And so we're left with the limit as x goes to 0 of x divided by the square root of x squared plus 9 plus 3, which is 0 divided by 6, which just equals 0. So this limit, once we do the rationalizing of the numerator, the limit equals 0. And we're going to look at a graph of y equals x squared plus 9 minus 3 over x. And I just put this in Desmos to sketch a graph of it. And there is a hole at 0, 0, because my domain says I can't divide by 0, so x can't equal 0 in our domain. And these are two examples of how we could simplify our expressions if we ever run into a situation where the limit looks like it's going to go to 0 over 0. So go ahead and keep practicing on problems like this, and it's going to get easier the more that you practice, and please visit with me when you have questions.